it's actually fun to watch it get erased. I mean, you probably, right? Isn't that the funnest part of the video? Just watch this disappear. So, chapter 7, it's called working with this new thing called the Laplace transform. Laplace transform. It's named after a mathematician, Pierre Simon de Laplace, another French mathematician. A lot of them were French, whatever. All nationalities do math, actually. It's the language of the universe. So the Laplace transform, the notation is this. Watch this. You do a Laplace transform of a function f of t, and when you do it, the answer is a function, we call it capital F of s. So when you perform this transformation on a function, f of t, the answer is f of s. It's a new function. You know, the word transform might be kind of new to you. By the way, let me just add this. Of course, I don't have to add this, but just to be very comprehensive, a lot of times we use the function y of t. What would you call big Y of s? Yes, thank you. Right. But that word transform might be new to you, but it's a... We've dealt with transforms before. We've just never really called them a transform. Guess what's a transform? Doing a derivative is a transform. You go from one function to another function, kind of the derivative of this function. But you know, you go from sine to cosine, or you go from tangent to secant squared. So doing a derivative is a transform, and the inverse of a derivative, or an integral, is a transform. You're transforming one function to his antiderivative. And when you see the original definition of a Laplace transform is this. And you'll see that it's really kind of just an integral. But it's not just an integral. It's a very specific type of integral. Check this out. The Laplace transform of, the Laplace transform of f of t is this. It's the integral from 0 to infinity of e to the negative st, that's an s. Sometimes my s's look like 5s, so watch out for these s's. E to the negative st, f of t dt. So this is what you do to this function. What do you do to this function? You stick it in this integral, multiplied by e to the negative st, and you integrate it from 0 to infinity. When it's all said and done, the answer will be some big capital F of s. It'll be, yeah. And so this is a little weird and abstract. Math is what it is. We're going to use it, the Laplace transform, to help us solve differential equations, is what we're going to do. But we're not going to go there quite yet. First, we're going to try to get used to this guy. We're going to try to do it. Let's try somebody. Can we do the Laplace transform of t squared? All right, well, here's what I should do. I should do the integral from 0 to infinity of e to the negative st times t squared dt. I should do this integral. By the way, I'm doing this integral with respect to t. The variable is t. So what am I doing with that s? I'm treating it like a constant. I'm going to treat the s like a constant. In the end, we're going to evaluate this integral from 0 to infinity, so all the t's will disappear, and we'll end up with just an answer that'll have s's in it. Thus, we'll have a function of s kind of as our answer in the end. But first step is, can you do this integral? And well, and another little concept is, what we got here is what we call an improper integral. When we go from 0 to infinity, we hit this in Cal 2 for a brief section or two there in Cal 2. You did an improper integral. Technically, you would make it proper. Do you remember how to make it proper? what's improper about it is that infinite bound, and so you would do the limit as a goes to infinity, and you would sort of replace that with infinity with the letter a. I mean, that's kind of subtle, and it's almost just notation in a way, but that's how you make an improper integral proper. And like I said, that was in Cal 2, it was in section 8, 7, kind of in the middle of calculus 2. All right, so that's what I'm doing. Now I'm going to try to do this integral, e to the negative st times t squared dt. Any suggestion how to do that integral? Good. I would call it integration by parts, but I would follow the shortcut for integration by parts called the tabular method. I sure would. So I'm going to go right over here and do a little tabular method here. Let's see. I'm going to call u the t squared, and I'm going to take the derivative 2t, and then 2, and then 0. That's how you do u and his derivatives. And then I need dv. The dv is that e to the negative st. And then technically what you're doing each step here is you're integrating. When you integrate e to the negative st, it should just be himself, but it spits out a negative 1 over s. Do it again. It's himself. It spits out another negative 1 over s. So how about a 1 over s squared, a positive 1 over s squared? Do it again. It's himself, e to the negative st, spits out another negative 1 over s, negative 1 over s cubed. This is doing integration by parts with the good old tabular method. Over here you put plus, minus, and then you grab these terms. These are terms that you grab like this. Here's your first term. Multiply all that together. That's your first term. Here comes your second term. Notice how you drop down that level over there. You drop down one level. Here's the third term. And this is the answer to the integral. The answer to the integral is, okay, how about negative t squared over s e to the negative st. That's that first guy. Negative 2t over s squared e to the negative st. Negative 2 over s cubed e to the negative st. How you guys doing? That's the answer to the integral. Wait a minute, that's the answer to the integral. Now the integral needs to be evaluated from 0 to a. After we evaluate it, we will then, lastly, take the limit as a goes to infinity and get an answer. But first we have to evaluate from 0 to a. All right, that means what am I doing? Sticking an A in there for what? For who? For T. Yeah. All right, I'm going to move over this way. Plugging an A in there for T. You know, by the way, I'm going to...
Just make it A.
You know what I'm going to do, though? I'm going to factor out that e to the negative st, so I don't have to keep writing it. So I'm factoring out the e to the negative st. So it'll be an e to the negative sa, if you don't mind. And then here I go. Negative a squared over s minus 2a over s squared, and a minus 2 over s cubed. Minus e to the negative sa. And now what am I doing? Plugging in a 0, right, you guys? Sorry, my A looks like a 9. My S's look like 5s. You got to watch out for that. That's an A. All right, that's an S. All right, now I'm plugging in a 0 for T. That's kind of nice. When you plug in a 0 for T, that's 0. That's 0. I did have this thing factored out. I'm sorry, I screwed up.
Yeah, that should have been okay.
I'm sorry. When I plug in a 0, that's e to the 0, e to the 0, e to the 0. There's really no need to factor it out now. It's e to the 0, and those are all 1s. Wait a minute, those are zeros. When you plug in a 0, that's a 0, that's a 0, that's a 1. I'm getting, what am I getting? A -2 over s cubed there. Are you guys okay?
Yeah.
Sorry about that. Dude, we're getting close here. Now, I'm done. I mean, I'm finished. It's kind of messy looking. This has got this E thing attached. The last step is I am taking the limit as A goes to infinity. And here we go. Now check this out. This is now, we got to go back to doing limits. We got to recall how to do limits in a way. But, you know, if I plug infinity in here, you know, it's infinity squared, negative infinity, -2, all over these s's, you know. I kind of feel like that's a negative infinity. Is that okay with you?
Yeah.
Infinity squared, negative infinity over it. I mean, I'm treating s like a constant still, letting a go to infinity, negative infinity. I feel like that's a negative infinity. But when you plug infinity over here,
0.
that's e to the negative infinity. And e to the negative infinity is a 0. Good. And so 0 times this infinity, well, technically, 0 times infinity is indeterminate, and you kind of got to figure that out. Hang on. But it's easy on this one. Listen, maybe I should drop him in the denominator. If I drop him in the denominator, what is he? He's e to the s over a. So I called that an infinity. I called it a negative infinity. I'm calling now, what am I going to call this? We called it a 0 a minute ago, but I just moved him to the denominator. I'm letting a go to infinity. Now I'm going to call it infinity. So it's infinity over infinity, which is also indeterminate.
Sure.
But I taught my students, who's the bigger infinity? Come on here now. We don't have to argue about this. Technically, if you have infinity over infinity, perhaps you should use L'Hopital's rule to help you prove the answer. But wait a minute. Who's going to infinity quicker?
Exponential.
The exponential goes to infinity much quicker. If the denominator goes to infinity much quicker, the whole thing goes to 0. Thank you. So this whole thing goes to 0. Minus a -2 over s cubed. What's the answer? Minus a negative, what's the answer? 2 over s cubed. That's the Laplace transform. What a pain, huh? That's the Laplace transform of what? Of t squared. The Laplace transform of t squared, after this long process, is this. You guys all right? It was integration by parts. It was a nasty little limit. It was, you know, a lot of little details in here. But we found this Laplace transform. We proved it. Here's the truth. You ready for the truth? I don't make you suffer long. You guys got a nice teacher. I only make you suffer for 5 minutes before I tell you the truth. The truth is, you might need to know this definition of Laplace transform. You might need to use it for me on a test. But most of all Laplace transforms you do by looking them up in a table. And there's a table in the back of your book. I printed out some tables I'm going to give you. Let me show you some of the most famous Laplace transforms. Here they are. The Laplace transform of a 1. You could go through that process and prove it to yourself, but I'm telling you right now, it's 1 over s. The Laplace transform of a t. You could go through the process and learn all about it and prove it to yourself, but I'm going to tell you right now, it is a 1 over s squared. We just did t squared, didn't we? Did we do t squared? We just did t squared. Let me show you the rule for t to any power n. The rule for t to any power n is this. N factorial over s to the n plus 1. That's the Laplace transform of any t to the n. So the truth is that we got this original definition, and we should practice using it a little bit. That's the first bit of homework in 7.1, wants me to use this a little bit. But very quickly we say, dude, memorize these. Well, wait a minute, we don't even say that. We say, dude, you don't have to memorize these. Look them up in the back of the book. Some of these famous ones you get to memorize. I mean, if you work on some homework and do this, you'd like to have them you'd like them on the tip of your brain. So you end up kind of memorizing some of these basic ones. But I'm actually not requiring you to. You get to have a table of Laplace transforms. You get to have that with you. Let's do some other famous ones. Here's one. The Laplace of an e to the at. Now, this is just any number times t. The rule is 1 over s minus a, I think. The Laplace transform of a cosine kt. Let's see, for cosine, I think cosine is a s over s squared plus k squared. I might should look some of these up myself. As you can tell, I guess I got them memorized, unless I screwed up here. The sine of kt. I think the sine of kt is k over s squared plus k squared. They're kind of different.
What's the main use for this?
Well, it's mental math exercising. That's the use of it. Learn to love it.
Really?
I just kind of wondering, like,
Now, well, we're in a differential equations class. Eventually, and maybe even by the end of the day, maybe not, we get to use them to help me solve a differential equation. So they are useful for differential equations. What you'll learn eventually here in a few days is they're actually particularly useful for piecewise differential equations. We've dealt with piecewise before, but they're particularly useful for piecewise differential equations. Yeah, so.
All right, thank you.
You're welcome. In fact, oops. Okay, I got my definition of Laplace transform. I just erased it. So I wrote down some. This is good. This is some basic Laplace transforms. I'm going to get back to some of these. Look, since I just mentioned that they're good for piecewise problems, let's watch this. Here's a function, f of t. It's going to be, here's what this function is. It's a 0 while t is less than or greater than or equal to 0, but less than 4. And it is a 1 when t is greater than or equal to 4. You guys with me? I just made up a function. A piecewise function. I made up a real easy piecewise function. But if I want the Laplace of this, let's try it. If I want the Laplace of this, it's kind of funny. I can't really, I don't know. I could focus my brain on the 1 and I could try to, but I think I better go, I don't know how to do that. I think I better go back to my original definition. And my original definition said, if you want to do the Laplace of something, you do an integral from 0 to infinity, e to the negative st, f of t, dt. Hold on, but my f of t is a piecewise function. And if I'm trying to integrate from 0 to infinity, do you realize what I probably have to do is break it up. I should go from 0 to 4. Good. And I go from 0 to 4. What do I plug in for my f? I mean, I got my e to the negative st, and what do I plug in for my f of t here?
0.
I plug in a 0. Yeah, that's kind of funny. Okay. Dt plus, and then I'm going to do this other guy from e to the negative st 1 dt, and I'm going to do him from 4 to infinity. I wonder how this is going to work. I'm not sure if I made up a good problem or not. Anyway, let's see what happens. This always confuses me a little bit. Let's just take a little time out here a second. You know, when you're integrating a 0, what's the answer when you integrate a 0? You do get a constant. You do. But there's another thing going on. Hang on. That's an indefinite integral. Watch. If you're integrating a 0, well, if you're integrating a 0 and you have bounds, like from -7 to 12, well then you might say you got a constant, but then you try to evaluate it from -7 to 12. By the way, you're sticking your -7 and 12 in for the variable x, which ain't there. And so when you plug in your 12, you get c. And then you plug in your 7 and you get c, and you subtract them. So then what do you get? You get a 0. And so there really is. All right, so hang on. When it was an indefinite integral, the answer was c. But when you put bounds on it, it really is a 0. It is a 0. I get a little confused, so I went and did that. But I'm going to suggest that that's what this is. This is a 0. Thank you. Because of the bounds. Okay, thank you. So now I got to work on this. This is not difficult over here. Oh, except technically, it's an improper integral again. You know, how do you make it proper, you guys? You do the limit as a, or you can use b, or, you know, c, or, okay, a goes to infinity, and then you're doing an integral from 4 to a. It's just it's kind of it's like being proper. You know, it's like using the right fork for your salad or something. You know, it's just, you can still eat your salad, but anyway, that's being proper about it. How do you, let's see, how do we integrate e to the negative st?
Negative 1 over s.
Yeah, negative 1 over s, e to the negative st. Okay, from 4 to a. I'm plugging those in for t. When I plug those in for t, I get negative 1 over s, e to the negative sa, minus negative 1 over s, e to the, I'm plugging in a 4, so e to the negative 4s. Now that's my answer. Hold on. Except I forgot something. I'm taking the limit as a goes to infinity. I really want these e functions to go away. Listen, well, when a goes to infinity, so I better put this up here. The limit as a goes to infinity. Okay, so here's what we said before. We did this before. We said that's a goes to infinity, but it's like a negative s time, so it's like a negative infinity, and e to the negative infinity is 0. Okay, that's what I want to happen. But let me make a little quick comment here. I kind of fudged through it last time. I got to make a comment here. For this really to be negative infinity, I want that s to be positive. I mean, if the s, okay, I'm plugging in an infinity. If the s was negative, that negative would make the s positive. I would end up with positive infinity, I think. And I don't want, that's infinity. I don't want I want this to go to 0. Like it does. But it goes to 0, but that s needs to be positive. So this does go to 0. But it's almost like when that goes to 0, well, this little statement has to accompany it. I mean, that s is greater than 0 is what makes that go to 0. And it's just a little statement. It's just a little, again, being picky and proper. That's kind of what I'm doing. If s is positive, I'm not changing the sign in front of s. I'm just saying s is positive. The negative in front of that positive number makes it negative infinity. And when a goes to infinity, it makes it negative infinity as long as s ain't negative. If s was negative, it would make it a positive infinity. Okay, so that's a 0. and I'm done. 0 plus this. So I get plus 1 over s e to the negative 4s. I guess that's my answer to this piecewise. What was the question? What's the Laplace of this piecewise function? And the answer is 1 over s e to the negative 4s. That's kind of interesting. That's what's kind of weird about these piecewise things. See, I couldn't really follow this rule. These rules didn't help me, you guys. On these piecewise problems, I kind of got to do it like this. And there's a couple of them at the beginning of the homework. I wouldn't do 12 of these. I would do
On the answer
2.
when you want to.
What'd you say?
On the answer when you want to touch the S.
So the answer should maybe have, all right, somewhere in this process, this little statement should be made by you, the doer of the integral. And you're saying maybe it should kind of accompany my answer here. And you're kind of right, yes. You're right. But again, it's not really going to be crucial to anything we do, but it is. It did. It's what makes that go to 0. By making the statement that he's got to be greater than 0 is what makes this go to 0, which is what we want. All right. Anyway, the Laplace transform is a transform. It's a transformation. It's a linear transformation. Again, you may not exactly know what that means. It is a linear transform, and here's what that means. I'll tell you what it means. It means if you're doing the Laplace of alpha times f of t plus beta times g of t, then the answer is alpha big F of s plus beta big G of s. Now, what the hell did I just say? I mean, this mathematical statement says this, you guys, all in one quick statement. It says, like you're used to with derivatives and integrals, you're used to this. You're allowed to take constants, alpha and beta are constants. You're allowed to take constants, multiplied constants, and sort of hold them out front and do the derivative of him, or the transform of him, plus, and if they're plus or minus together, by the way, it's plus or minus, maybe I should put plus or minus, that you're allowed to do, what I'm trying to say is you're allowed to do the Laplace of each one of these separately and add them together. Do you understand? And not only that, you're also allowed to pull multiplied constants out front. Oops, yes. I'm pulling the beta out front. Are you okay with that? All right. So that's what I said in one quick fancy statement there, that you're allowed to pull constants out front and you're allowed to do separate terms, added and subtracted separate terms, the Laplace of each term separately, and pull constants out front. Right, that's what this says. That's what a linear transform can do. That's true. It's kind of a mathematical thing that applies to a lot of things. Of course, maybe we should have known that. We know that it applies to derivatives. We know that it applies to integrals. And essentially, at its gut level, a Laplace transform is an integral. It is an integral. It's a very specific integral, but it's an integral. So, okay, you guys, now you're ready. Now you're ready. Okay, so I'm going to give you a Laplace transform chart that has all possible Laplace transforms on there. But right now, you can just go with this chart. And can you do the Laplace transform of this? 6t to the 4th minus 8 cosine 5t plus 6e to the negative 7t. Sure. By the way, we're not going to do the original definition. We are not going to go do an integral. No, we're not. We're going to do these guys. Bam, bing, boom, we're done. How do you do a t to the 4th? How do you do a t to the 4th? First of all, you step right past this. So first of all, you realize I'm allowed to do 3 separate Laplaces is what I'm doing. And if there's any constants, I just kind of slip them out in front of the front there. So I'm slipping the 6 out there, and I'm doing the Laplace of t to the 4th. 4 factorial over s to the 5th? Okay, awesome. That's how you do it? Is that how you do it?
Yeah.
T to the 4th? Yep. With the 6 out front. By the way, 4 factorial is 4 times 3 times 2 times 1. It's 24. 24 times 6 is 144. 144. So this is 144 over it. No big deal, but you should clean them up a little bit for me. We can wait till the end and clean it all up. What is this? This is an 8 multiplied by the Laplace of cosine. What's the Laplace of cosine? Here it is. It's an s over s squared plus 25. Do you agree? With the 5 there, that's what you get. And that's an s. And like I said, I warned you, watch out for your s's and your 5s. Be careful.
Cursive.
Maybe you should write little cursive s's, but I hate that. Yeah, it's all right. Next, an e function. There's a 6 in front of the e function. I'll pull it out, and I'm doing e to the negative 7t. The rule says whatever a is, it's 1 over s minus a. So it's 1 over s minus negative 7. So how about s plus 7? Are you okay with that? Okay. Like I said, I wanted to clean these up. There's really not a lot of cleaning on these. 8s over s squared plus 25. 6 over s plus 7. And you're done. I don't like to try to get a common denominator and add this together. Somebody might. We do get that issue. We get some nest. We get some. If this was a common, if somebody wanted to get a common denominator and put this together, it'd be kind of a mess, and I don't want to do that. But what would the denominator be? S to the 5th times s squared plus 25 times s plus 7, and then some crazy numerator. But I want you to think about that denominator a second, because you know what happens? What does happen to us? What we start to do is I'm teaching you how to do Laplaces. Okay, what we start doing is we start doing Laplace inverses. So now I start giving you this and asking you to do a Laplace inverse. Not a big deal. We just got to, but we better practice them forwards first. I mean, we practice doing them forwards, but then we start sort of doing them backwards. Like we look him up and try to get back to this. We look him up and go back to this. We look this up, we go backwards. We start doing backwards. And what if this was all together and had one big common denominator? What do you think you need to do to get back to this? If somebody had put it together with a common denominator, I don't want it. I want it back like this. How do I get rid of how do I decompose something with a common denominator?
It's not A, B, D.
I use partial fraction decomposition. That was taught to you in Cal 2. You used it to integrate. Remember that? I might need some partial fraction decomposition. I'm not a huge fan. It's kind of a pain. Partial can be a pain, but we might need it. It's a skill we might need. Boy, how can I make this any tougher? Here, let me see. Can I do, let's try this guy. Can you do the Laplace? You guys are smart. Now watch this. Can you do the Laplace of this? T plus 6 squared. I mean, you're looking over here, and you might say, man, I don't see nothing that looks like that. Right? But you're right. Like I said, I knew you guys were smart. You could figure this out. Right. There is nothing over there that looks like that, really. And you can't adapt and make your own rules very easily. So what you suggested was you FOIL it out. Yeah, and that's what you do. And you got 3 different terms, and then you do it. I don't really have to do that, but I could. Let's t squared plus 12t plus 36. Okay, so now I can do the Laplace, I think. The Laplace of the t squared is 2 factorial, which is a 2. 2 factorial is a 2 over s cubed. You guys know about factorials, right? Yeah. You know what a 5 factorial is? 5 times 4 times 3 times 2 times 1, right? Okay. 12t. Well, that's a positive 12. 1 over s squared. That's what t is. See, I get a little confused. Sometimes I think t is this, but it's not. T is 1 over s squared, and a plain old number is a 1 over s. You with me? Sometimes I get my brain's just thinking weird. But so t is a 1 over s squared. A 36. How do you do a 36? 36 over s. Right. Right. So we're done. Unless you want to call it common denominator.
No.
All right. Yeah, let me see. I'm trying. I can't. I'm trying to. How do you make this more difficult? I want to make it more difficult. Yeah, you can't make it too much more difficult. All right, so that's good. Here, I got more to say. I'm going to keep talking. I might do some Laplace inverses now, which takes me into 7-2. But in order to do Laplace inverses, let me give you this. This is in the back of your book, but I made a copy for you. So it's front and back. It is 58 Laplace transforms. Now, we don't use all 58, but we use the first 10 or 12, and then sometimes up in the 20s and 30s, and then there is some stuff in the, I mean, we use some scattered amounts of this stuff. So well, no, you get to bring this to the test. You get to have it on the test. But you do kind of start becoming familiar with it, kind of, and how it looks and how you find things on here. So, so as I ease into 7.2 then, I'm doing a Laplace inverse. So it's called Laplace inverse. And so now when I do the Laplace inverse, it'll be the Laplace inverse of some f of s, and it'll bring me back to f of t. You know? So let's see, can we try one? Let me try one here. The Laplace inverse of, watch this, this is cool. This is cool. Right off the bat, I don't mess around. I do not mess around. All right, so start looking in your chart for somebody that looks like that. I'll check back with you in 20 minutes. I mean, you got your chart, or you do have, this is a partial chart right here. You got 58, you got 6 up here on the board. You got 58 in your hands. But the truth is, there's nobody that really looks like this, exactly like this. But if part of this chapter is you got to be very algebraic. You got to kind of know how to change things, bust things up, like you did this. I mean, that was an algebraic idea. Let's foil it first. Now you can do it.
Complete the square?
Nah, completing the square is something I'm going to need at times, but that doesn't apply to this. You know, that denominator makes me think of sine or cosine. See that how it looks? See it? S squared plus 30 plus, you know. But the numerator doesn't. The numerator's pissing me off.
Oh, you can split it up into
Oh,
and sine.
brilliant. Split it up. It's, you know, I added 2 things. Yes, exactly. Brilliant. Think of it as a 4 over s squared plus 36. Let's do that Laplace inverse, and then let's do this Laplace inverse. Exactly. Exactly, exactly, exactly. Now again, there's a little more to this now. Let's see. So what is this guy? This has got this s squared plus 36. I'll tell you, let's do the second one first. Let's do the second one first. This has got this s squared plus 36, and he's got an s on top. So The one with the S on top is the cosine. The one with a number on top is the sine. That's a big difference there. See that? K is a number, S is the S, you know. So anyway, I'm looking at the second one now, and I'm saying that's a cosine. Now, what can I do with the 3? I can just pull it out. So it sits out of my way, and then it's a cosine. Okay, so it's a cosine, what are you saying, 60? Cosine 60. With a 3 out front. Good job. All right, so now I'm thinking this other one is a sine. It's a sine 6t. But wait a minute. To be a sine 6t, it's got to have a 6 on top. Well, you make the necessary adjustments. Again, you do get very algebraic. You can make that a 6 if you multiply and divide by the appropriate thing. You can make it a 6. The real way I like to do it is this. I like to just, rather than fix the 4, here's how I like to do it. I like to pull the 4 out. The 4 is out, so now I'm left with a 1. Now, what do I want that to be, though? What do I need it to be or want it to be? A 6. Okay, then I'll multiply by a 6 to make it a 6. Now, I can't just multiply by a 6 unless I go out front and divide by 6 or multiply by 1/6. In the meantime, the 4 is out there too, by the way. But did you see that? I pulled the 4 out of my way, put the 6 up there, as long as you multiply out front by a 1/6. So now what's the final answer? I got the 6 up there, and so I do got a sine 6t, and what's the result of what's out front is a 2/3 or a 4/6 or a 2/3. You with me? So it's a little thinking goes into these little problems. I mean, you know, you got to do some manipulation, some algebraic manipulation. They're good problems. That was a good one. I mean, that was a good one. I didn't mess around. Here, what about this? The Laplace inverse of 5 over s plus 2 minus 8 over s to the 3rd plus 16 over s squared plus 11. Dude,
First one's
I love this stuff. Algebraic manipulation. I'm a good manipulator. Evil manipulator. All right. What is this first one? So yeah, you say it's easy. You're kind of right, I think. You just pull the 5 out of your way, and it's an E function. It's just, what are you thinking? Yeah, I think it's actually e to the negative 2t. Isn't it? Because if this was a negative 2, you would put it in here and you would have s plus 2. Right. Right. So it is e to the negative 2t, and the 5 was just on top. We just pulled it out front, and so it's just out front. Yeah, that was easy. All right, what's the next one? The next one has this s cubed in the denominator.
2t to the 2.
Oh, so if you got an s cubed in the denominator,
2t to the 2.
it's a t squared. Okay.
4t to the 2. 4t to the 2.
Oh, wait. Right. All right, yeah, you're onto something. You're saying it's a t squared, and if it's a t squared, what needs to be on top?
2.
A 2 factorial, which is a 2. And so you're suggesting that I sort of pull a 4 out, is what you're suggesting. I pull a 4 out, and I leave the 2 there, and now that is classic t squared. I got you, with a 4 out front. Whew, that's tricky. Sometimes it's trickier than that. That one was kind of easy. Pull a 4 out, leaves the 2 there. Right, so that's 4t squared. Okay. All right, what about this next one? S squared plus 11. That's an 11 in the denominator, you guys. S squared plus 11. I mean, that makes me think of these denominators. That's what these are. S squared plus 11. So what's K?
Can you bring out 16 multiplied by the square root of 11?
Yeah. You're onto it, something. I mean, right. If there's an S on top, you're heading for the cosine guy. But without the S on top, that makes it a number on top. And if it's a number on top, you're headed for, it's a sign. So ours, there's no S on top, so ours is a sign. And it is the sign of the square root of 11t. That is what it is. So that means I wish I had a K on top, and K would be the square root of 11. So how do I manage getting that square root of 11 on top?
16.
I pull the 16 out, I throw the square root of 11 on top, which means I have to divide by the square root of 11.
Okay.
And already the 16 is out front, so I'm doing this in my head, but you're following me, I think. I'm left with a 16 over a square root of 11 out front. Is that what you're saying? Good job. Cool, we did a Laplace inverse. Are you ready for this? Let's do this one. Let's do another one. A Laplace inverse. This might not be too fun here. A Laplace inverse of this. S over S minus 2, S minus 1, S minus 3. I want to do this Laplace inverse. I want to look in I got a chart of 58 things I could try to look up and try to do this Laplace inverse backwards. The problem is nobody in my chart, it looks like this. I could look at all 58. I could make you look at all 58. I could be patient, make you suffer. Anyway, there's nobody like this. So here, this is a classic example. Again, I don't know how well you recall partial fraction decomposition, but I would like to do partial fraction decomposition on this. Let me help you. So I'm kind of coming out to my scrap paper here. What we're doing is we have an S over S minus 2, S minus 1, S minus 3. I guess I could have done that in some kind of order. And I want to decompose it. Now, I remember the rules of decomposition. I feel like I need to tell them to you, though, so listen to me. Let me see here. See, what we're doing is, this is weird. A lot of times you have different denominators and you want to get a common denominator and get something together. Well, we're doing the exact opposite. I got a common denominator and I want to decompose it into individual denominators. And so what individual denominators are out there that would add up to be this common denominator? Well, it's kind of obvious. It would be somebody with a denominator of S minus 2. It would also be somebody with a denominator of S minus 1, and it would be somebody with a denominator of S minus 3. I mean, those three denominators, somebody could get a common denominator, add that crap up, and give me this. And what the numerators are some unknown constants that I'm going to call A, B, and C. And it's true, dude. It really is true. If you added up these guys and got a common denominator, there is an A, B, and a C such that you can add this crap up and get S over this. I mean, there exists an A, B, and a C such that if you added this up, you would get this. Now our job is to find that A, B, and C. That's decomposing this fraction. Here's how you do it. First, you got to know how to set it up, and that's how you set it up. Then you multiply by this common denominator. When you multiply by this common denominator, it's s minus 2, it's s minus 1, it's s minus 3, and you cancel it right here, and it's all gone, and you're left with s. Over here, you're multiplying by s minus 2, s minus 1, s minus 3. The s minus 2 cancels, and it leaves you with a times the other 2. Are you guys following me? Over here, same thing. I'm going to be left with b times the other 2. Did you follow that? I'm multiplying by the common denominator. I'm canceling where it's appropriate. Over here, I'm left with c times the other 2. S minus 2 and s minus 1. That's an s over there. And then you play different kinds of games to help you find A, B, and C. The classic game you play is this. You let S be something very convenient. Like, let S be a 1. That's very convenient. If you let S be 1, what happens is you get a 1 on this side. That's a 1. But what's cool, watch what happens. When S is 1, what happens to this whole term?
A and C.
It's zeroed out. That whole term is zeroed out. You get a b times negative 1 and negative 2. I think I did that right by plugging in a 1.
Yep.
That's positive 2b equals 1. Divide by 2. Guess what b is? 1/2. All right, just repeat that process a couple times and you'll get A and C. Do you remember doing this?
Yes.
Let S equal 2. Let S equal 2. That means on this side it'll be a 2. And then over here, that'll be a 0, and that'll be a 0, so I'll be getting a 2 in here. That'll be a 1. That'll be a negative 1. I think I get a negative A. So I'll multiply by a negative sign, and A is negative 2, I think. Finally, I think we should let S be 3. When you let S be 3, that means it's a 3 on this side. And then over here, that's 0, that's 0, that's a 1, that's a 2, that's a 2C. If you divide by 2, C is 3/2. So what you just did was you decomposed this fraction so it has a lot different look now. It is, instead of S over that common denominator, it is A over this, B over this, and C over this. A is a negative 2 over S minus 2. B is a 1/2 over S minus 1. C is a 3/2 over S minus 3. And you can do the Laplace inverse. These are the easiest little guys you've ever done. And I knew it was headed to this. I mean, I just knew, I know how these things work. And you do too now. You kind of know that all these multiplied linear factors can be decomposed into individual linear factors. So when I'm staring at this, I see a bunch of E functions. But in order to get it, I gotta go through the steps of decomposing it to get to that. I mean, I knew I was headed toward that. I just had to go through the steps to get to that. But here we go. The answer is negative 2 e to the 2t 1/2 e to the t 3/2 e to the 3t. Again, very algebraic. You haven't seen me do a derivative or an integral, and I might not for a while. This Laplace stuff is very algebraic. Listen, I'm going to tell you one more thing. We got 10 minutes before we leave. I'm just going to show you one more thing. I'm still in 7.2. And if I had a few more minutes, if I could almost solve a DE with you, but I'm not going to quite make it that far. I don't think I want to. I don't think I want to do that today. But in order to solve a DE, you got to learn one more Laplace transform. You got to learn how to do the Laplace transform of a derivative, y prime. Now, hang on just a second. Do you know how to do the Laplace transform of a y? Do you know how to do the Laplace transform of a y? Well, wait a minute. Whoa.
Y over S.
See,
Y over S?
hang on, hang on. When I started today, by the way, so we were doing Laplaces, then for a few minutes we've done some Laplace inverses, and that we're getting ready to solve a DE, but before I can solve a DE, I got to teach you how to do the Laplace of a y prime. But hang on, I think I lost you a little bit here. Let me make sure of something. In the very beginning of today, I said when we're doing a Laplace of a function f of t, we call that big F of s. I mean, this is just kind of abstract talk. There's not a specific function there, and there's not a specific answer there. Okay, so, and then I said, well, what if it's a y of t? And then it's big Y of s. Okay. Anyway, that's kind of what I meant by this. Okay, I forgot to put the little t, but y is a function of t. So treat y like the independent variable. Don't treat him like the dependent variable. Well, wait, I just screwed that up. Treat y like the dependent variable, not the independent variable t. So it's not like a 1 over s. So the Laplace of a y is, I'm saying, is big Y of s. I'm saying it's this. I just forgot to write the little of t. Okay, so what about the Laplace of a y prime?
Big Y prime.
No, it's not that easy. It's weird. I mean, no, it's this. It's S big Y of s. It's S times big Y of s minus the initial condition y of 0.
I was going to say that.
Did I even do that right? This is, what is this one? This one is number 54. But in number 54, they do an nth derivative. Hang on a second. For number 54, when I look it up, I don't even want to do it. Never mind. Hang on a second. Let's get back to this. That's a y prime. How do you do a y double prime? Watch this. I think it's s squared big Y of s minus an s y of 0 minus a y prime of 0. See, what's funny is these are initial conditions. I mean, the initial conditions from the DE are showing up in my Laplace of the DE. Did you hear that? The initial conditions from the DE are showing up in my Laplace of the derivatives in the DE. And there's a pattern here. You know, when you had a first order DE, you always only had one initial condition. When we got to second order DEs, we started to have two initial conditions. And it builds from there. If I wanted to do a y triple prime, I would get s cubed big Y of s. Now watch what happens. This s cubed starts to drift down, s squared, but then the initial conditions start to jump on here. And then I get an s, y prime is 0, and then the s's are gone, but I got the last initial condition there. See that? See how that is? There is a pattern to this if you can decipher it. In number 54, they tell me how to do the Laplace of the nth derivative of t. By the way, and they use, instead of y, they use f. I'm going to use y. And so how do I do it when it's an nth derivative? I got to do s to the n big Y of s minus s to the n minus 1. Right, he drops a power. Oh, and then the initial condition jumps on there. Minus, he drops another power. The next initial condition jumps on there. Minus dot, 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 dot. Eventually, there's 1s, and there's
Raise to the n.
y.
Just y to the n. Like 0.
N minus 1 prime of 0. Hold on. And then finally, that's not the last one. The last one, the s is gone, and you're looking at the nth derivative of 0. Is that right? Did I do that right? Hang on a second. No, I screwed that up. When it's a y triple prime, the last initial condition is a y double prime. So hang on. This should be a n minus 1. This should be an n minus 2 here. Good God. I bet that's what they wrote. Is that what they wrote? Kind of, yeah. Actually, they didn't write as many terms as I did. They wrote the first one and the last one. They didn't write any of this other stuff. But the truth is, you don't have to try to decipher this nth derivative, although you can decipher it. It is just this pattern. And in reality, when you do problems, you're going to do first derivative, second derivatives, maybe a third derivative, maybe a fourth derivative, but I kind of doubt it. I mean, this is, you know what I mean? These are the derivatives that we've seen in our DEs. We don't really have a 10th derivative usually. If we did, I would go try to do that pattern. All right, so I'm out of time. I'm at the end of 7-2, sort of. And I'll see you Thursday. And you can try a little 7-1 homework, maybe a little 7-2 homework. I'll try to grade stuff.